Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over equilibrium problems, and in particular we're going to focus on how to take advantage of those extreme equilibrium constants where you either have a very large equilibrium constant or a very small equilibrium constant and you can neglect x. And so in this particular video we're going to look at x is small, and you start with lots of reactants and none of at least one product. So you're going to have at least one product that you don't have any of, and then you have a very small equilibrium constant. So how do you solve that sort of problem? In other videos, I'll talk about other situations, but we're going to focus on small equilibrium constant with zero product, or at least zero of one of the products. So let's get into this. Okay, so here we have a generic equation, equilibrium, in equilibrium, and we're going to start with some concentration of our reactants, and then we got zero product. And in this case, we're given a equilibrium constant of 4.0 times 10 to the negative 8. So this is very small. And so remember, let's remind ourselves that the equilibrium constant is equal to the product over the reactants. Products over reactants. So what the equilibrium constant is telling us here, since this is a very small number, this means that the amount of product is very small and the amount of reactants is very large, relatively speaking. And so this means that this ratio is really small. What does that mean? It means that at equilibrium, this reaction is going to produce very, very little products because this is a small number. So the numerator is very small while the denominator is very large. And so that means that at equilibrium, this is going to end up with a tiny amount of product, very little product. And so we are going to use that to our advantage to help us solve equilibrium problem, or this particular type of equilibrium problem, much more easily. So let's go ahead and set up our ICE table. So if you remember, ICE stands for initial, meaning starting, and then you have C for change, and then E for equilibrium. So we start with the concentrations in the beginning. So what we start with, that's I. And then we look at the change of the concentrations, and then we look at the equilibrium, or what the concentrations of our species are at equilibrium. So here we are starting with this as our initial concentrations. So A, 0.50 molar, B, 1.00 molar, and then C and D are 0. So in this case here, because our products are 0, or at least one product is 0, that will tell us that this is going to shift towards the products. It's going to shift towards the right to make product, because you can't have 0 product or 0 reactant. So if you have 0 on one side or the other, you know it has to shift to that side. So here, since we have 0 of C and D, we know it's going to shift towards C and D to make C and D, because you can't have 0 here, right? So, and again, that would be true if, let's say, if I had 0.5 molar for D, but I had 0 for C, it would still shift in that direction because I have 0 of C, and I can't have 0 amount of something at equilibrium. There's got to be something there. So, excuse me. So let's go ahead and set up our ICE table. So this is I. So that's our initial concentrations. And then for the change, we know it's going to shift this way. So we're going to lose a certain small amount. We're going to use X to identify or represent what that amount is. And it's got to be stoichiometric. What does that mean? It means that whatever the coefficients are here, we're going to have to multiply that by those coefficients as well. Again, what does that mean? Let me clarify. So I know here that if I use up A relative to B to make C and D, for every one B that I use, then I need two A's to combine and react to form C and D, right? So whatever I lose of B, I'm going to lose double the amount of A because of the way it's set up, because of the balanced equation. So if I lose 2 of B, or if 2 of B react to form C and D, I need twice as much A to react with that amount of B. So if I used up 2B, then I'm going to have double the amount of A. That would be 4. And I'm going to create 1 C and 1 D. So if I use X as a change or a certain amount of change, then I'm going to need to make sure that it's balanced according to the ratios that I have here, according to the coefficients in my balanced equation. So if I make B, if I'm going to lose a certain amount, let's call that X, as I've been saying, during the equilibrium, during the reaction when it goes this way, I'm going to lose a certain amount of B. So we call that X. So I'm going to minus X. I'm going to subtract a certain amount. I'm going to lose a certain amount of B. Well, if it's an X amount of B that I lose, and I know that I'm going to lose a double amount of A, then I'm going to lose here 2X, right? So here I lose an X amount, here I lose 2X amount, double that amount. And then over here, I'm going to create an X amount. So here I'm losing an X amount. So this is 1 to 1 to 1. So the ratio should be the same. So if I lose a certain amount here, well, I'm going to gain the same amount over here because I'm making product and it's 1 to 1. So I'm going to gain an X amount here, and that means I'm going to gain an X amount of D. So I gain an X amount of C and D, I lose an X amount of B, and I lose double the amount of A, negative. I lose 2X of A. And now I can set up my equilibrium expressions. So that would be E for my ice table. And so all I do is I add these together. So it's going to be 0.50 minus 2x. And then I'm going to add those together. So it's going to be 1.00 minus x. And then I add these together, but 0 plus x is just x. And here, 0 plus x is just x. So now I have my concentration expressions at equilibrium. So these are what the concentrations of A, B, C, and D are at equilibrium in terms of x. So now that I have the expressions here, I have to, again, let's go back and remind ourselves that we're trying to find out how much x is at equilibrium. And given that we have a very small equilibrium constant, that means that reactants here are favored. It means we're going to have a whole lot of reactants at equilibrium and an itsy-bitsy tiny amount of product. So not very much product is going to be formed, and we can use that to our advantage to simplify our equation. So let's go ahead and set up our K expression, our equilibrium constant expression. So as I said, it's products over reactants. And in this case, we're going to have few products. So here, this is very few. And this is going to be a lot. Okay, so let's set this up. So remember, it's the concentration of the products over the concentration of reactants raised to their stoichiometric powers, right? So in this case, KEQ is going to be equal to the products. So the concentration of C, the concentration of the products, concentration of C raised to the power of its coefficient. So the coefficient is 1, so we have a 1 there. We don't write ones. Multiplied by the concentration of D raised to the power of its coefficient. Its coefficient is 1, so there's a 1 there. We don't write ones. And then this is going to be divided by the concentration of the reactants raised to their powers of their coefficients. So if I do A, concentration of A, the coefficient here is 2, so that's going to be squared, power of 2, multiplied by B. So we have the concentration of B, and then again, its coefficient is 1, so raised to the power of 1. So here's the equilibrium expression of this equilibrium equation, this reversible equation or reaction. So now I have my equilibrium constant expression. Now I can take these equilibrium concentration in terms of X and plug them into this equation here. And what I get is, since C and D at equilibrium, those are going to be X. So I'm going to put those concentrations in as X. So it's going to be X times X. So C and D multiplied, X times X, over, well, A, this is the equilibrium concentration expression for A, 0.50 minus 2x. So that's going to be down here. So that's going to be 0.50, minus 2x. And then multiplied by B, and B has the concentration in terms of X of 1.00 minus X. So I'm going to put that in. So multiplied 1.00 minus X. And so now I have my KEQ expression all in terms of X. So now normally what you would do at this point is you would jump in and you would start solving this equation, getting X to one side, maybe having a quadratic formula of some sort. But if we think about the situation we're in with regard to the fact that KEQ is small, and then the fact that, well, we're not going to produce very much product, we can simplify this expression to make the calculation a lot easier. So here, again, going back to the fact that this is a very small number, meaning that the ratio of products to reactants is very small, meaning that very little product is formed. So we start with 0, we gain a certain amount, but that certain amount is going to be, or assumed to be, really small because of the small equilibrium constant. So what does that mean? Let me put it in these terms. So we have to compare the X value that we have here with the original concentrations, right? So here, if we look at X here, with regard to the concentration, we want to know how small is this? Well, let's make up some numbers here. So let's say that we have a concentration like 0.50. So let's say we take 0.50 molar. Well, what would a small number be with respect to this? So let's compare a couple of other numbers. So if I take 0.0002, right, we would say that that is a small number compared to this one. Or if I write this number here, so if I say, if I compare it to, let's say, 1. So this number relative to 1 is a small number, right? But what if I compare that number to 0.0000000001? Oops, I went off the board. Zero point zero 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 one. There you go. Okay, so this number compared to 1 is a small number, but this number compared to this number is a large number, right? So we have to figure out how small is our X value compared to the original concentration. If it's small enough, we can ignore it. So for example, let me take this number here, right? So if this was X, if X was 0.0002, and I subtract that from my original concentration, let's subtract 0.0002 from this, and I'll get 0.4998 molar. Okay, so a small difference. Now, if we take into consideration the fact that we are doing measurements here and we're subtracting measurements, we have to keep in mind significant figures, right? So remember the rule for subtraction, when you're subtracting measurements, the rule is that your answer should have the same number of decimal places as the least number of decimal places, as the measurement with the least number of decimal places. So here I have 2 decimal places, here I have 4. So I need to cut my answer down and round it to 2 decimal places, but look what happens when I do that. So here's 1, 2, I cut it off there. Now I have to round, and I end up rounding it back to where it was before. So the point there is, if your change is small enough, it's going to be so small to be negligible that it won't really matter. You can effectively say that it's not going to make a difference in your original concentration that you started with. Well, why is this so important? Well, it makes the calculation easier. Now, notice here that I have here's my expression again. And so I have 0.50 minus 2x, and I have 1.00 minus x. So if we can make the assumption that x is negligible, meaning that it's so small that when we subtract it from our original concentrations, that it's not going to have really any effect at all. So just as if I subtract this from 0.5, I end up pretty much with 0.5 anyway. So if we can assume that x is too small to make any effect or any difference in the original concentration, that the original concentration is really going to stay pretty much the same. So if we make that assumption, we can cancel out the x's here, because remember, we're subtracting this amount from this, and we're assuming that by subtracting this from this, it's not going to make any difference really. So we end up with this anyway. So here we're subtracting x from 1.00, and we're assuming that this is so small that it pretty much stays the same. So we're just going to ignore it and cancel it out. Now you'll notice up here we have x times x. This we cannot ignore, this we cannot cancel out, because we're not subtracting these x's from anything. We're not subtracting them from a concentration. So these we cannot cancel out. These we can, because we are subtracting them from a certain amount of concentration, and we're assuming that that's not going to make any difference. It's not going to have an effect on the concentration, the original concentration. So we can get rid of those, and lo and behold, it gets the equation here, KEQ, right, which is equal to 4.0 times 10 to the negative 8. So we'll write that in 4.0 times 10 to the negative 8 is going to be equal to x times x, which is x squared, over 0.50 times 1, or I'm sorry, oops, I forgot one thing. I forgot the squared here. Don't forget the squared. Sorry about that. So this should be a squared. This should be squared as well. So this is going to end up being 0.50 squared multiplied by 1.00. And so now we can more simply solve for x squared by just dividing, or multiplying the bottom here by this, so we can multiply both sides. So here, let me get some room over here. So then I'm going to multiply, well, this times 1 is just going to be 0.50 squared, right? So then if I fix that, that would be x squared over 0.50 squared. And then I can multiply both sides. So this is going to be 0.50 squared. So multiply that side. And then I can multiply this side as well. So I'm going to multiply this by that. So let me write that up here. So I'm going to have 4.0 times 10 to the negative 8. That's going to be multiplied by 0.50 squared, right? And so remember, this cancels out. So now this is going to be equal to x squared, like so. And now I can solve for x, take the square root of both sides, so square root of that's going to be equal to x, because the square and the square root cancel each other out. And then I take the square root of this here. So to find x, all I need to do is take the square of that, multiply it by that, and then take the square root of everything. And when I do that, I get 1.00 times 10 to the negative 4 molar. So this is x. So basically, this is the change that we were talking about with regard to our ice table. So here, this is the change x, and we ended up with x concentration. So this means that the concentration of C and D at equilibrium is going to be 1.00 times 10 to the negative 4 molar. So as we said, a very small concentration. Okay. So, however, we had to make an assumption to get that concentration to simplify the calculation. And that assumption was that x, 2x, and x are so small as to be negligible, and it's not going to really have a very big effect or big error in our calculation if we make that assumption. But the question is that true? Can we make that assumption? How do we know? Can we check it? And yes, we can check it with what is called the 5% rule. So the 5% rule is that your assumed x, or whatever it is that you're subtracting, should not be more than 5% or more of the original concentration. So its error cannot be more than 5%. If it's 5% or more, then it's an illegitimate, invalid assumption to make. If the error is less than 5%, then it's a valid assumption to make, and you can go ahead and make it. So how do we do that? So let's go ahead and go back to our ICE table here. Again, we are taking away 2x amount away from 0.50, and here we're subtracting x from 1.00. So we got to first ask ourselves, well, which one do I use to do the 5% rule? Well, you want to take the one that's going to give you the largest amount of error, because if that one gives you the error, then if that one passes the test, then the other one's going to pass the test as well. So which of these is going to give you a larger error? So you'll notice that here we're subtracting a larger amount from a smaller amount, and here we're compared to this one. So here I'm subtracting x from 1.00. Here I'm subtracting double that amount from a smaller amount, 0.5. So that means that this here should give me the larger error. So I'm going to use this to do my 5% rule. Well, how do you do the 5% rule? Well, let me show you. So I'm going to go ahead and erase this, since we don't need this anymore. So the 5% rule is basically, I'm going to take the x amount and I'm going to divide it by the original concentration, and then I'm going to multiply it by 100 in order to see what percent of the x amount, or the amount that I'm subtracting, what percentage is that. So basically it's going to be the change divided by the original concentration multiplied by 100. So since I'm using this, the change is the 2x, right? The change is the 2x here. So I'm going to take the 2x and I'm going to divide it by the original concentration, which is the 0.50. So I'm going to divide it by 0.50, and I'm going to multiply that by 100, and I'll get my percentage. So the x here is what we calculated it to be. So we're going to plug that in as well. So then we take, that's going to give us the percentage. So we're going to take 2 times the 1.00 times 10 to the negative 4. And we're going to divide that by the original amount, which is 0.50, 0.50. And then we're going to multiply that by 100. And that's going to give us our percent error that would be due to making the assumption that this is too small or is negligible to really count for anything. And when I calculate this out, I get, let's see, 0.04%. So this is much, much less than 5%. So that tells me that the assumption that 2x is so small as to be negligible and therefore ignored is valid. And so now I can go ahead with my, and accept this as the concentration of C and D at equilibrium. So now we can state that at equilibrium, the concentration of my species of my reactants and products are going to be 0.50 molar for A, 1.00 molar for B. Why? Because we assumed that these are going to be so small that, again, subtracting them is not really going to change the original concentration. So the original concentration is the concentration at equilibrium. And for C and D, since they are both X, they're equal to each other. So both C and D are going to have this concentration at equilibrium. And that, ladies and gentlemen, is how you can take advantage of this extreme situation. And again, in this situation, we're looking at where X is really small and one of your products, or at least one of your products, is 0. And so how do you go about solving this type of problem? So anytime you have an X is very small situation, where your equilibrium constant is really small and one of your products is 0, you can use this methodology to help you solve that problem. And that, ladies and gentlemen, is it for this video. In a future video, I'll talk about other situations in which you might be able to use or be able to neglect X. And so stay tuned for those. But if you enjoyed this video, if this was helpful and you learned a lot from this video, then please, by all means, like the video, share the video, hit that like button somewhere over there. Also, make sure you subscribe to the channel, hit that notification bell. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.